Hello everybody, and welcome to this live coding session on the Manning Books Twitch channel. My name is Tanmay Bakshi. Thank you everyone for joining in today. Before we begin, just a little quick introduction about myself. My passion is to work with technology, to build technology, and of course I like to do this on a wide variety of platforms, Swift and the sort of Apple ecosystem being one of the main platforms that I target, and specifically I work with a lot of different AI, sort of machine learning, deep learning technologies as well. Now, what's really interesting about this is that not only do I love building this technology, I also love being able to take that technology that I build and make it more accessible to different developers, which is why I'm holding this stream today. And precisely because of my book, Hello Swift. It's a great resource for kids to, or really anybody, including kids, to get into the world of programming in general and to do so by learning how to build iOS apps. And so through this book, I teach you, by example, how exactly you can start from scratch and learn how to build your own iOS applications. And through that, you end up learning all the basic concepts of programming, computational thinking, problem solving, these sorts of things. And so that's what this book is all about. Now, what we're going to be doing today is we're actually going to be taking a look again at the Swift programming language, but specifically, we're going to be implementing something a bit more advanced than what we get into in the book. So if you take a look, this book teaches you all the fundamentals of Swift. It teaches you programming, it teaches you, iOS app development, and at the very end, we stop at around SpriteKit. And so I teach you how to do like some relatively complex 2D graphics work. From there, though, there is still a lot of scope as to more stuff that you can do with the power of Swift and with the power of the frameworks that Apple gives you. And so today, we're going to be taking a look at a very specific framework called CoreML. Now, what exactly is CoreML? Well, CoreML is a framework that's built by Apple and available on all different Apple platforms. And the idea is to make it easy for developers to incorporate machine learning technology into their applications using the very powerful hardware that Apple gives you on their devices. Now, first of all, before we even get into that, what is machine learning? Well, what I'm going to do is show you just a really quick example of what machine learning, deep learning technology does. And again, this is going to be super interactive, so I do have the Twitch chat open. If you have any questions, feel free to put it there, and I'd love to answer them live. And of course, if you do have any other questions, feel free to put them in the author forum after this, and I can go ahead and answer those as well. But apart from that, feel free to ask any questions. I'd love to go ahead and answer them. And now let's go ahead and take a quick look at what deep learning technology is all about, why exactly we would need a framework like CoreML to run that technology on our phone, or on really any iDevice, and then let's go ahead and take a look at how we can implement some relatively complex, but I would say really fascinating technology made simple by CoreML. Specifically, these are called language models, but we'll get into that in just a moment. So what I'm going to do now is I'm going to go ahead and share my screen, and what I'm going to do is I'm going to open up a playground, or what's something called the Tensorflow Playground. This is something that you can open up as well live as we go ahead and do this, and you can actually play around with it as I do, and so Tensorflow Playground. And so as I play with this, again, feel free to do so as well. But just really quickly, the reason that I've opened up this thing called the Tensorflow Playground is because this is almost like an environment. Actually, if you've read the book, you know what a Swift playground is. And essentially, a Swift playground is where you can play around with different Swift tools and Swift code so you can figure out how your code works in real time. And, well, the Tensorflow Playground is something similar, but for neural networks, which are a kind of machine learning algorithm. And if we were to take a look at the TensorFlow Playground here, what you're seeing on screen will make a lot more sense if I give you a bit of a description as to what exactly a neural network does. Well, the idea is that let's just say we have, two different data sets, say X and Y, and we know that there's some sort of relationship between them. And so, if you have X, then it's plausible that you could predict Y based off of X. But we don't know how to do that mathematically. So let's just say I were to give you a picture of a dog or a cat. Let's call that X. And your Y would be, well, what is this? Is this a cat or is this a dog? And you can't really make a mathematical function to do that because as a human, we can't really mathematically describe how we recognize different things visually. That's not exactly easy for us to do. In fact, that's not really possible for us to do, or else it would have been done. But with a neural network, what we essentially do is we offload that task of building that mathematical function to the computer. And so now, instead of us having to, sit down and write the mathematical function that's able to go into X and figure out what Y should be, so for example, take an image and determine if it's a cat or a dog, suddenly the computer can do it for us now. And the Tensorflow Playground is a highly simplified version of similar technology that lets you sort of visualize how these neural networks work. And then once we visualize that, I'll go ahead and show you how we can port this over to iOS and actually use it on an iPhone. So let's go ahead and take a look at that. Now, on screen right now, within the TensorFlow Playground, one thing that I'm going to do before we even start, and I'll explain why we're doing this in a moment, is reduce the hidden layer count to just 1 and the neuron count to just 1 as well. So now you should just have 3 lines. These might be different colors for you, but you should have 3 different lines, 2 from this side of the screen to the middle, and then 1 from the middle over to the end. Now, essentially what's happening is on the left is your input to your neural network, which is essentially, again, your mathematical model, your machine learning model that's able to convert input to output. Now, what happens is the input that we're feeding in 2 different sort of inputs to the model. One of them is called X1. And essentially the idea is that if a certain point on the graph is more towards the left of the graph, like over here, for example, this dot over here, if it's more towards the left, then X1 for that point is going to be more negative. It's going to trend towards -1. Whereas if it's the opposite side, so for example, if say this dot over here is towards the right, it's going to trend to +1. So if I highlight X1, you should see that the background towards the right is blue, towards the left is orange. That means orange towards the left is -1. That's sort of where X1 activates as -1, and towards the right it activates as +1. In the middle, you can see that transition area where it sort of merges and bridges through a 0 in between, like when X is 0, X1 also is 0, and then negative and positive towards left and right. And then the second input that we feed to the network is just similar, except it's positive towards the top and negative towards the bottom. And so what that does is it sort of gives us information for both left, right, and up, down, but through 2 separate inputs to the machine learning model. Now, what I'm also going to do is, just to sort of make this a bit easier, I'm going to switch the data that we use over here to the Gaussian data. This is an easier data set to work with, and I'll explain why in just a moment. Now, this node over here, this node is actually very interesting because it's what's called an internal or a hidden node of a neural network. So what that means is that we don't know exactly what this neuron is calculating. What we do in order to calculate its value is we take our 2 inputs, we multiply them by these things called weights, and then we sum together those weighted inputs, and suddenly we've got the value for this neuron. All right? Now, how exactly do we determine those weights? Well, that's the secret sauce behind machine learning models. That is what we use some complex mathematics to figure out, which luckily is mathematics that you don't need to care about because of the way that we're going to be training our models today. As a matter of fact, the goal for this neural network is to be able to make it so that behind all of the orange dots in this graph, there's an orange background, meaning so the network predicts that, at this location the dot would be orange. And behind all the blue ones, we want a blue background. So the neural network is predicting that for these dots, they're more than likely blue. That's the goal. Currently, it's kind of flipped. So you can see we have a almost vaguely orange behind the blue and a vaguely blue behind the orange. But when we click the play button to start training the neural network, suddenly, as you can see, it pretty much instantly figures out the pattern that orange or dots on this side of the graph are usually orange, dots on this side of the graph are usually blue. Now, really quickly before we move on, I do want to say that the input that you feed in really does matter in terms of how your network is going to perform. And so, for example, let's just say I were to only feed in the left-right xy, then, well, the neural network doesn't have enough data to draw a diagonal line. It can only really draw the line straight up down, which in this case works, but if one of these dots was slightly more towards the left or slightly more towards the right, that wouldn't have worked well. Similarly, if we only feed in the up-down data and not the left-right data, then as you can see, it sort of misclassifies this one dot because it's almost an outlier. But then when we feed in both pieces of data, look at that, the network is able to use both and create a much better line in order to separate those two pieces of data. It doesn't seem like much, but when you scale this up from left, right, up, down to pixel values in an image, and when you scale from dots on a graph to labels of what's in the image, then you get really, really powerful results. Like when you actually open up your phone, for example, and when you talk to Siri, or when you open up your phone's photos and it tells you whose face is in whose photo, it's powered by very similar mathematics, machine learning tech. Really quickly before we continue, just because this is really interesting, and of course if there are more questions about this, feel free to put this into the Twitch chat. I will go ahead and answer them. One more thing that I want to mention really quickly is that this dataset in particular was really, really easy for the neural network to adapt to or to learn from. And that's because the data is what's known as, in mathematical terms, linearly separable. And so just a single straight line between these two datasets would split the two, sections of data perfectly, a single straight line. But then there's oftentimes data sets where the data is not what's known as linearly separable. So for example, this data over here. It's impossible to draw a single straight line and perfectly separate all the data in this graph, because if you were to draw it diagonally, then, well, you have some blue on one side, some orange on the other side, and so on and so forth. Even, horizontally or vertically, you can't do it. And so right now, if we were to use our simple two inputs, left, right, up, down, and a single neuron in the middle and click on play, we don't get very good results. The network is just kind of trying to fit to something, and better than nothing at least. But the reason for that is because we only have a single neuron in the middle, and single neurons are only capable of modeling linear relationships. And so what we need to do is we need to add more neurons so that it can capture more a sort of more rounded interpretation of the space. So let's just say we add another neuron. In theory, we should see two straight lines now. So approximately something like so. But it's still not particularly complex. So if we wanted to be able to draw more complex lines, then what we can do is add another layer of neurons. Now we've got two neurons in two layers, and all of these weights again are figured out automatically by the math. We click on play, and suddenly we're drawing much more complex lines. And so that is machine learning technology in action. Now, in this relatively simple example, we can go ahead and count the number of weights that we have. So we have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we have 10 weights that are helping us decide what the output for the model should be. But here's the issue. 10 weights is nothing. For this really simple example, 10 weights is more than enough, right? We do not need more than 10 weights. That would be overkill. I mean, I could easily go ahead and add another layer, maybe some more neurons, and it would be really good at the task. As a matter of fact, sometimes they're actually bad. As you can see right now, there are just too many weights, and the neural network is actually having a hard time because there are too many weights to contain all that information. So sometimes that's not a good thing. But then as we work with more complex data, sometimes it becomes necessary. Like this data set over here is way more complex. We've got like a circle of blue in the middle surrounded by a ring of orange. This requires a more complex architecture, but still these numbers of weights are nothing. As a matter of fact, if you were to take a look at some of the larger models in the industry, we can get up to hundreds of millions, even billions, and the largest hundreds of billions of weights. That's a lot of weights. And so you need a lot of compute power in order to process all of those weights. And as a matter of fact, I would say that pretty common nowadays, you've got models that go into the hundreds of megabytes worth of weights, which is again a lot of data to work with, a lot of compute that needs to be done to figure out what the machine learning model is trying to say. And that is why Apple built CoreML. Because as a programmer, you shouldn't have to worry about, oh, how exactly am I going to take my weights and compute with them really efficiently and make it so I don't take up too much power, but at the same time it's really fast for the user to work with. This is the kind of stuff that Apple engineers worry about so that you don't need to. Another really great advantage is that within the iPhone, you've got special chips, like for example, the GPU and the neural engine, which are little processors that are dedicated towards making it faster for you to do machine learning inference. So, when you take a machine learning model just like this one or more complex, and you export it to CoreML and then feed it into your iOS application, they're able to automatically use all of those chips and make it super, super fast. So now that we've talked a lot about CoreML, how about we actually take a look at it in action? First thing we're going to do is we're going to open up this website called Write with Transformer. Now, Write with Transformer is a website from a company called Hugging Face. It's a pretty incredible website and actually powered by some pretty incredible technology too. Essentially, what Write with Transformer does is it's an online demo of these things called transformers. Transformers are sort of like the state of the art when it comes to dealing with language with machine learning technology. Because, I mean, think about it. Language is really, really complex. You could have a sentence like, I shot an elephant in my pajamas. And what does that mean, right? As a human, maybe with some context, you could figure it out. But in order for you to understand what that sentence means, again, you need the context. Right? It could mean that you're a photographer and you're taking a picture of an elephant while you're wearing pajamas. Or you could be hunting an elephant while the elephant is wearing your pajamas. As a matter of fact, one of the most creative interpretations that I've heard at a research conference that I was at, actually, was that you're wearing pajamas and there's little pictures of elephants on the pajamas and you're taking pictures of your pajamas with the elephants on them. And so there's all sorts of interpretations you can have. And so writing mathematical functions in order to actually figure out what exactly a sentence means is impractical. So we need machine learning or deep learning technology to help us do that automatically. And the Write with Transformer website helps us demo or take a look at or interact with that technology as well. I see a wonderful question from Optimized on the Twitch chat. He's asking, what's a transformer? I will be getting into a bit more detail on that in a moment, but I'll actually go ahead and sort of show you or tell you what a transformer is as we go ahead and try it out. So what I'm going to do is I'm specifically going to take a look at a model called GPT-2. It's from OpenAI. And I'm going to click on Start Writing, and I'm going to delete the text that's already in there. And let me show you what a transformer does, and at the same time I'll tell you what it is and how it works. So let's just say we were to take a simple sentence like, I'm currently demoing some really amazing technology, right? Now, what this transformer model is trained to do is it's trained to take all of the text that I wrote, so all of this text on the left, metaphorically, and it's supposed to take that and predict what the next word would be in this sentence. Then, after that, after it predicts the next word, that's fed back into itself. And then it predicts the next word. And then that's fed back into itself, and it predicts the next word, and so on and so forth. This is called an autoregressive language model. All right, so let's just say I go ahead and click tab at this point. What's going to happen is the neural network is going to take a look at the text that I've already written. It's going to predict the next words word by word. So as you can see, it says the top two sort of next predictions are, I'm currently demoing some really amazing technology on the demo floor, so stay tuned for more, and I'm really excited by what I've got. So I can just select whatever I want to, and then I can keep hitting tab, and it's going to keep going ahead and printing more and more text. And as you can tell, this is pretty good text. I mean, it's saying, I'm also very excited to bring my own experiences of using the system to the community. That makes so much sense in context. Of course, as we continue to generate text, it might degenerate a little bit, like it might not continue to be as high quality as we expect it to be. Again, this is a neural network. I mean, we got to cut it some slack. It's a deep learning system. But again, it is writing really good text for a computer standard. Now, really quickly, I'm going to go ahead and answer that next question. What is a transformer? So if you think about natural language, you might think of it as what's known as a time series of data. So, like for example, the word amazing. The meaning of that word depends on and is changed by all of the words that came before it, and in some cases, even the words that come after it. But for now, for the sake of simplicity, let's assume that it's just the words before it. Now, in order to really understand what amazing means, you first need to understand all of the words before it and what they mean in context with each other. So traditionally, what we would do in the world of deep learning is we'd use these things called recurrent neural networks to understand this kind of data. And recurrent neural networks basically look at the word I'm, and then they create this little internal mathematical state of the word I'm. And then they look at the word currently and the previous state, and they combine them, and they're like, okay, this is my new state. Then they look at the word demoing and the previous state and combine them, and so on and so forth. And it keeps combining that previous state with new mathematical representations of each word. And they sort of go along the whole sentence word by word like that. But that is incredibly inefficient because you're looking at it word by word, right? Like for example, when you're processing the word really, you're not allowed to start processing the word technology until you've also processed amazing. And so computationally, it's really, really inefficient. The CPU is capable of processing hundreds of words at the same time, but because the recurrent neural network is only looking one word at a time, well, you can't really use your CPU to its fullest potential, and it takes a long time to compute that sequence. And so that's why I believe researchers at Google wrote a paper called Attention is All You Need, which is where they introduced the transformer architecture of neural network, which, again, it's a neural network kind of like what we saw on the playground, but way more complex. It's got all different kinds of operations within it, but at the end of the day, it mostly just boils down to matrix multiplications. And the way it works is by essentially looking at the entire sentence or the entire sequence at once. And what it's doing is it's combining every word's representation with every other word's representation. That might seem a little bit more inefficient. Like if you could just look at it word by word, why would you want to do, every word against every other word? Doesn't that make it more inefficient? But no, actually it doesn't, because today's computers are capable of processing all of that data at the same time. So transformer technology is pretty incredible, and it is sort of the state of the art when it comes to understanding language with the power of computers. Also, another question from Powerman, or not a question, but he's saying, is this something similar to what Google is using in their Gmail app now, where it auto-completes your sentences? You're absolutely right, it totally is. It is incredibly similar to that technology. As a matter of fact, I would not be surprised if they are already using transformers under the hood in order to do that for their Google Smart Compose feature. And so that is... as a matter of fact, I'm pretty sure they do. That's probably why they invented that technology. That's why their research teams were working on it in the first place. So yes, it is incredibly similar technology. Now what we're going to do is we're actually going to go ahead and implement this transformer model on an iOS app. And we're actually going to be able to generate similar text in iOS. I think it's going to be really interesting, and feel free to, again, ask me any questions if you've got them along the way. First thing I think we should do is go ahead and prepare a simple Swift application that will act as the almost template that we're going to use and sort of integrate our technology into. So I'm going to go ahead and create a new Xcode project. I'm currently on the macOS Big Sur beta, but if you're not, no worries. These steps, because of the sort of frameworks that we're working with, should be pretty much the same. The only thing that might look slightly different is your user interface for Xcode. But apart from that, most of what we're doing today should be the exact same. So of course we're going to be building an iOS application, so we're going to click on iOS app. I'm going to call this, let's call this auto typer. All right, let's call that. And we're going to be using Swift UI as our user interface framework today. So I'm going to go ahead and put this onto my desktop. and we're gonna get started here. Now, the way that Xcode works nowadays is instead of giving you a storyboard and putting the different UI elements on there, we're gonna be coding the user interface with actual Swift code, which is way easier when it comes to more complex user interfaces, and you'll be able to take a look at some of that today as well. So let's think of a good UI for this. I'm thinking we put a little text field on the top of the screen, and the text field then has a button under it. When you click on the button, it goes ahead and uses the GPT-2 language model to go ahead and compute the next words in the sentence. And there's another text field at the bottom which fills out what the model sort of wants to extend your sentence as. So for that, I guess we start off with a text field. So let's see, yes, SwiftUI does have a text field element. We can give it a title and some text, which I will go ahead and show a preview of the view as well in a moment once we do that. But then again, a text field is only a single line, so let's go ahead and do a text view, which unfortunately has not yet been bridged over to SwiftUI, so we are going to be using a text field. Let's just give it a title as... let's just say we want to feed in some seed text, all right? And the text that we put into the text field will be stored in a variable called seed. So we're going to create a state variable called seed. It's going to be of type string. This is really interesting because in SwiftUI, all you need to do is create a string and sort of tell Swift that it's a state variable, meaning that it's interacting with the user interface. And suddenly you can pass that seed over to the text field, and instead of having to store the text field as a variable, you only store the text within it as a variable within your view. So now we go ahead and let's just say we give it a default value of a blank string, build it. It should build successfully, no syntax errors, and show a preview. All right, wait for the preview to show up. Right as it does, though, we'll be able to see that in the middle we have of our little view. In the middle, we have a text field where the placeholder is called seed text, and then right as we enter some text in there, we should be able to take a look at the text. All right, it says failed to build content view. Let's see why that is. Failed to build auto view because it can't import autotyper. Well, let's try just cleaning the Xcode project, and maybe now we'll be able to preview properly. Ooh, still does not want to preview. Well, let's just go ahead and run this on the simulator, and we will more than likely just be able to take a look at the interface within the iOS simulator. Again, in the book, I do show you, how you can actually go ahead and use different ways of running your application, whether that be through the iOS simulator or on an actual iOS device. So if I go ahead and just extend the simulator view a little bit so we can actually see it. There we go. We see it's currently booting up. Give that just a moment to go through. And then right as that boots up, I will show you the user interface. Until then, let's go ahead and continue coding what this UI needs to look like. So under the text field, as I mentioned, we're going to have a button that right as you click it, it goes ahead and fills out the rest of your text based off of what the transformer thinks it should go ahead and fill out. So I'm going to go ahead and embed this in something called a vertical stack, which will enable me to stack multiple UI elements vertically. And then right under that, I'll put a button. With the button, we should just put in some text. So let's just say we put a title. Let's call it Generate with GPT-2. Oh, there we go. Our iOS simulator is launched. Give it a moment to actually start the application. Sometimes that takes a minute because of how the simulators work. But until then, let's just go ahead and continue to code. So when you actually click on the button, what I'm thinking we should do is call a function called generate on the actual view itself. So we're going to create a new function called generate, and this is where we can handle the generation of text with GPT-2, which is something that we still need to implement. All right, so as you can see in our simulator, we do have the seed text field, which is currently stuck towards the left, and in order to solve that problem, we can just put some padding on the V stack, which will give us a little bit of space towards the left and the right and top and bottom. So we've got the text field, we've got the button, And right after the button, we're going to put another label. So we're actually, in SwiftUI, labels are just called text. And the text that we're going to be showing, let's just call it generation. And so we're going to create a new state variable called generation, and this is going to store what the neural network actually generates, which we will go ahead and show with this text. All right, let's just go ahead and see. All right, so what we need to do is actually put this within a string because, SwiftUI requires you to pass a string to text. Let's just make sure that actually builds. No, it doesn't. Let's see what it's telling us. No exact match is in call to instance method append interpolation. Well, simple way to fix that. We don't need this to be a binding. We just need this to be a regular string because text isn't going to modify this, and so we don't need to do any real interpolation. So now, let's just go ahead and quickly take a look at what our UI looks like. So I'm going to rerun this in the simulator, and then we'll go ahead and implement the actual transformer technology. All right, as you can see, launched pretty quickly this time. We've got our little text field where we can enter seed text, so I can be like, this is a simple sentence. And then we click on generate with GPT, and in theory, once we implement the actual transformer library, then we should see the label populate over here with the text from the transformer. So now let's go ahead and do that. And in order to do this, we are going to need, well, two things. We're going to need to install Python, of course, and on Mac that comes by default. Nowadays, luckily with Python 3, since Python 2 is nearing end of life, or actually I believe it has already hit end of life. But along with that, you're going to need to install two separate libraries. So if I go ahead and open up my terminal over here, you're going to need to install CoreML tools is one. So the reason you need CoreML tools is because that's a library by Apple that enables you to actually deal with transforming your neural network models into CoreML format. And then apart from CoreML tools, you're also going to need Torch, which is actually PyTorch, which is a neural network library in Python, as well as Torch Vision. So Torch Vision is just another package that comes along with PyTorch and has a bunch of utilities to help you implement deep learning algorithms more simply. So you're going to be using CoreML tools, Torch, Torch Vision, as well as this thing called transformers. So this is, again, a package by Hugging Face. Transformers enables you to deal with the sort of cutting-edge language models really, really easily. So instead of having to implement all of that yourself, you can just use the implementations that have already been made for you by the experts over at Hugging Face. So go ahead and install all of these. I've already installed these because it takes a little bit to install, so I don't want to have you watch paint dry, so I've already done that for you. And once you go ahead and do that, then you're also going to want to git clone a couple of repositories. One of them is called Swift CoreML Transformers, and it's also by Hugging Face. Once you go ahead, what you're going to want to do is run a git clone of this repository, and then after you've done the git clone of that repo, then go into the repo. So we can just cd into it, and then within that folder, you're going to see a couple of different folders. One of them is called model generation, and so you want to go into model generation, and if you take a look, there's already a file called gpt2.py. Now, there is a bit of a catch here, and so I will explain that in a moment. I see a question from Powerman2824. Could I build this environment on a Linux virtual machine? Absolutely, you can. This part of the experiment, which is the actual creation of the model itself, the CoreML model, yes, you can do that on Linux. But then when you actually want to develop the iOS application and deploy to an iPhone, that is when Apple's ecosystem comes in, and that's when you have to use a Mac. You cannot use a Linux machine for that, unfortunately. At least, not yet, and it doesn't seem like Apple's going to want to let us do that either for some time. But regardless, you can do this section, which is the sort of Python end of things, on a Linux virtual machine. Oh, okay. If you're on a Windows machine, well, again, you cannot unfortunately actually implement the iOS tools, so you're not going to be able to code the iOS application itself. But the part of the environment that's responsible for converting the Python model to a CoreML model that iOS can understand, that you can do on a Linux VM on your Linux machine. You could more than likely, if you're on Windows 10, use the Windows subsystem for Linux. That's super high performance. That's a great way to do it. Otherwise, if you actually have a Linux VM, then you can do that too. So both should work. And of course, if you have any issues or any errors, anybody, feel free to put that in the live chat, and I'll go ahead and sort of help you out to fix that. Okay, so within this file of code that you've gotten from the GitHub repo, what you're going to see is there's actually quite a bit of code here that deals with transforming this model into something that CoreML is happy with. As you can see, some of the code is a little bit dirty. Comment from one of the code creators, I hate this. So there's unfortunately quite a few different workarounds that you've got to do in order for this to work, but at the end of the day, it gives us the result that we want, and that's really all that matters. So if you take a look at what's going behind the scenes here, there is one single, there is one small modification that you're going to want to make. By default, when you clone the repository, it's using a slightly older version of transformers, and so this is not going to be here. This line over here is going to be slightly different. And so what you want to do is where it says for transformers import, you want to modify that to from transformers dot modeling gp2 import. So make that small modification, and then you should be good to go. All right. So once you've done that, you should be good to go ahead and actually run this script. So I'm going to go ahead and invoke that script. Again, I'm running this on Mac. You could quite as easily run this on Linux as well, as long as you've got all the different dependencies installed. And then as you run this, what's going to happen is first it's going to go ahead and download the actual models themselves. So the raw PyTorch versions. That's around 0.5 GB. So again, these are really big models. So I've already gone ahead and done that for you. And also, really quickly, I will, just to sort of let you know, towards the end of the stream, I will be showing you some more interesting examples of what you can do with CoreML that's pretty unique, that you can't do with a lot of other libraries, and we will take a look at that in a moment. But for now, as you can see, I go ahead and run the script. It converts the model from PyTorch to CoreML format. It goes through all of these different layers, all the different 11 layers of the model automatically. And then if I go back a directory, and then I go into the resources directory, you can actually see that just now at 12:37, which you can confirm the time is 12:37, it wrote a file called gpt26412.ml model. What this means is that we took a small version of GPT-2 essentially and converted that to CoreML because, I mean, we don't want to deal with the really large versions of GPT-2 at the moment. If we were to take a look at the actual size, we see this is around 622 megabytes. And that's the small model, all right? So these models can get really, really big. This is more than 0.5 GB that we're going to be putting on an iPhone. So we'll take a look at that. And then once we handle this, then I'll also show you how you can make these sizes smaller. So we'll talk about that in just a moment. For now, though, don't worry about the size. That's just how it is, and we will deal with it momentarily. So what you're going to want to do first, though, is open up this resources directory. And so this is where Linux, unfortunately, will stop working because we got to open up Xcode again. So open up Xcode, open up your little file browser on the left here, and you're going to want to take the ML model file that we just made and drag that into your Xcode project. Give that a moment. Oh, do I need to do this the old-fashioned way? Ooh, okay, so drag it into mission control, and then there we go. So I'm going to drag the ML model into here, make sure copy items is checked, and then click on finish. Now what's going to happen is Xcode is going to slowly but surely take your ginormous model and put it into your Xcode project. I know it looks like nothing is happening, but that's just because Apple, for some reason, doesn't give us a progress bar. Xcode is currently working on copying in the CoreML model. The reason this takes a moment is because you're not just copying. Xcode is also now looking at the CoreML model, and it's automatically generating a bunch of Swift code that deals with actually, providing input to the model and taking output from the model, and it's doing a bunch of boilerplate code generation as well. So give that a moment. That's going to take a little bit to copy in. There's not much that we can do to make this faster. Now, another thing that you should keep in mind, oh, there we go, it just came in. But yeah, another thing that you should keep in mind is that this is Big Sur, which I believe after macOS Mojave, Apple started to use Apple file system, and because of the spec of that file system, copying files is super fast. So it wasn't the actual copying that took that long, it was Xcode just processing this huge model that took a couple of seconds. So we got this model in Xcode now, and as you can see, we can go ahead and see what sort of operations are being run within this model. So we've got 96 different transpose operations. We've got 49 and 49 of the scale and inner product operations. We've got rank preserving reshape, all these different operations within the actual model itself. And Xcode gives us this nice graphical way of viewing what the individual operations are that are being done within the model. So this is what Xcode allows us to see. We can also take a look at the predictions as to what the input and output of the model actually is, and the different utilities. So for example, let's just say you want to encrypt this model, and so what that would let you do is make it so that people that have your application can't just take the model out of the application and use it in their own applications. And so Apple will actually help you encrypt your model as well, so that you can keep your own intellectual property your own, even when you ship it on an iOS device, as well as what's called a model archive, which enables you to put a CoreML model into the cloud so you don't actually need to have it on the device. So quite a few different interesting features, but we're not using any of them today because today we're focused on getting a really good text generator on an iPhone. That's our goal. So let's go ahead and continue to code. Now, yeah, I see PowerMan just mentioned those are pretty awesome tools. Indeed, they are. And I haven't even gotten to my favorite yet. So you're gonna want to stick around because this is it's gonna get really interesting in just a moment. So now we've got the actual model in the code now, but now we need some sort of code to deal with the model itself, and to actually feed it the input that it expects and take the output and decipher it and tell our code what it means. Really quickly, I'm going to take a bit of a detour, a bit of a tangent, and go back over to the Write with Transformer website. So I'm going to do that here. And really quickly, just so you know, before I told you that these sorts of natural language pieces of data could be thought of as time series, right? So you could use recurrent neural networks to look at I'm and then look at currently and so on and so forth, and it would be able to understand the text. However, the issue with that, or not necessarily the issue, the advantage of that is that the recurrent neural network is able to model the time or the sort of order of the words themselves. So for example, if you take a look at I'm and then currently and then demoing, when you mix in the state of demoing with the state of I'm currently, you're able to sort of automatically learn mathematically that sense of order. But then with a transformer, since every word is interacting with every other word, transformers inherently don't really have that sort of sense of order. There's no way for a transformer model to determine if the word technology is at the end of the sentence or the beginning. The mathematics are the exact same regardless. And that's an issue because in natural language, order means a lot. And so what happens is when you feed in your input, the way the transformer models for language models work is instead of just feeding in technology or just feeding in amazing, you actually sum the mathematical representation for the word amazing with the mathematical representation for the position of that word in the sentence. So, if, for example, you have the word I'm, because it's in the beginning, you're going to sum the mathematical representation for I'm with its position, and currently, and so on, so that you're essentially shifting every input vector by a certain amount based off of where it is in the sentence, giving the transformer a sense of order. And that's why, when you take a look at the predictions over here in the CoreML model, you see there are actually two inputs. One for the input IDs, which is, what word were we fed in, but also another input for the position IDs, which is going to tell you at what position was I fed this specific piece of text. So that's why we have two different inputs. Another question I see, are we building this environment on an iPhone? So in case you're asking about write with transformer, yes, we are. The goal of this live stream is for me to show you how to rebuild something similar to this on an iPhone. However, the actual coding, of course, is happening on Mac for iPhone. So that's what we're doing. Okay, so now we've got our CoreML model in the application. Now we've got to write the code to deal with it. Luckily, we are using the transformers library, and so a lot of this is actually already done for us. So if we actually go ahead and take a look at this, all I need to do now is go ahead and take from the sources directory in the repository that I've already already cloned, and take these three GPT-2 files and drag them into my Xcode project as well. So just like that, drag them into my Xcode project. Go into mission control if macOS will let me, and then drag in my files. All right, there we go. And then I can take a look at these code files. They're pretty simple. It's just implementing the sort of prediction logic for GPT-2. There are three more files that you're going to need. You're going to need utils, ML multi-array plus utils, and math. So go ahead and take these three files as well and drag them into your Xcode project. Just like so. All right. So now if I go ahead and clean, or let's not even clean, let's just build. If I go ahead and build the project, you should see that we get no errors, and it looks like it is all working. Oh, we get one error. What is that error? Okay, it's because it cannot find the model name in this scope, but that's completely fine. We named our model something slightly different, so I'm going to go ahead and copy the name of the model file, and then go back into this file and change that name. All the dashes are replaced with all the dashes are replaced with underscores. So replace the dashes with underscores, and then we've got successfully compiling code. All right. And as you can see, we even get our simulator running that code too. Okay, so now that we've got our code running, we've got to actually go ahead and call GPT-2. Now, the way we're going to do this is by calling the code that was very nicely written for us by the folks over at Hugging Face. Now, we're going to go ahead and instantiate a new GPT-2 instance. Let's just call this GPT. And then we're going to call a function from within it. Let's see what that function is called. If Xcode's not going to want to predict or do code completion for me, I guess I'm going to have to do it. So we're going to call something called the generate function, and it's going to take some text. It's going to take the number of tokens that we want it to generate, and then the callback. So what I'm going to do is GPT-2.generate, and what are the parameter names? Text and callback. So I'm going to pass it some text, and that's going to be the seed. And in the callback, we're just going to take some text, and we're going to do self.generation equals text. Now I'll explain the logic a little bit, and then I'll go ahead and explain why this works and some other slight modifications that we need to actually get this to work. So basically what we're doing is we're creating a new instance of the GPT-2 model within this function. And then what we're doing is we're telling it to generate some text, and we're giving it the seed text to base its generation off of. Then we're giving it a callback function, which is a function that we pass to the function, which is then called every single time another word is generated. So instead of just generating 10 sort of words at a time and then just printing out all 10, it'll actually show you as it generates in real time, word by word. So every time it passes you the text, we go ahead and put that text into the generation string, which is shown on screen. Now, one thing is that this may be, no, actually, never mind. I thought that this would execute in a background thread. Luckily, that doesn't happen, and so we do not need to do any dispatch queue magic. So now, watch this. In theory, right, as long as we didn't hit any errors, I should be able to just go in here and type in maybe something along the lines of, I love deep learning technology, and now generate with GPT, and let's see if it does anything. Ooh, we get a bit of an exception. What is this exception? It cannot find 2 files that it needs. We forgot to drag in 2 of these files. Well, let's go ahead and do that now. So I'm going to go ahead and stop the application. I'm going to go over to the repo that we copied, go into resources, and we're going to get GPT-2 merges and also the vocab.txt, or sorry, GPT-2 vocab and GPT-2 merges, TXT and JSON. We're going to go ahead and drag those into the Xcode project. So I'm going to take this, put that into the Xcode project, like so. So what this does is it gives our application information about how exactly the machine learning model expects its input to be structured. So I'll go ahead and run the code once more. Let's take a look at the simulator. I love deep learning technology, and generate with GPT. As we can see, it's working hard. We can actually take a look at what Xcode tells us, and it looks like it's generating, but it's not updating the text in real time. So we'll fix that in a moment. But for now, just take a look at the fact that there we go. So the network generates, I love learning of, oh, that's actually pretty exceptional. So I said, I love deep learning technology, and it generated, and I love learning about it, which is right. I love learning about deep learning technology, and I hope you do too. But that was the neural network actually generating text through CoreML. I think that was pretty incredible. But the only sort of limitation now is that we do not see the text updating in real time. And the reason for that is because this sort of changing of the text is happening on the same thread as the generation of the text. And that takes so much compute power that we don't end up getting the time to change the text on screen. So what I can do is actually call something called dispatch queue and go into the global queue and asynchronously run this code. And what's really interesting is that iOS makes it so easy for me to just say, I want this code to run in the background. And just like that, I've got code running in the background. And when I want to run some code on the main thread so I can update the UI, it's, again, just like one extra line of code, and suddenly I can do that. So I love deep learning technology. Let it generate. I believe we should see it updating in real time now. There we go. So it says, and I'm excited to see how it can, and then that's where the generation ends because it's only supposed to do 10 tokens. But that is incredible. We already have a machine learning model that can generate text, and that took us less than 30 minutes to do. The fact that modern technology and modern infrastructure like the Transformers library and PyTorch and CoreML and Onyx, all of these tools are working together in the perfect way to allow us to implement this cutting-edge technology in under 30 minutes. All right, so now let's go ahead and take a look at the at some extra sort of features that CoreML enables us to implement. So as you can see, we've already got generation figured out, but how about we go ahead and let it generate more text? As a matter of fact, infinitely, as much text as it wants. Well, we're going to slightly modify the code from Hugging Face. So I'm going to do, instead of for I in number of tokens, just while true. And then what we can do is just... We don't need to print out the status, so I can just remove that. And we don't need to return either, since we've already got a callback, which means that in my content view, I don't need to discard the result from the generate function. So go ahead and build that. Let's go ahead and see. There we go. It builds. Let's go ahead and run this code now. All right, so we see it's asking us for some seed text, and it's going to let us generate with GPT. Let's see what we get. So I love deep learning technology. All right, let's see what it gives us. It says, and I'm excited to see how it can help us learn more about how to use it. Interesting. So it's able to generate some pretty competent text. All right. All right. So now this is actually really interesting. You're about to see a limitation of deep learning technology, and I want to see if you can identify what's wrong with this text. Let's see if you can figure it out. I'll give you a second. You might notice that this text is just the same thing being repeated over and over and over again. And now the neural network model is stuck in a loop of just generating dots. And so why is that? Well, first of all, we have to answer a more fundamental question. If these neural network models are just mathematics, then shouldn't we always get the exact same text from a neural network model? I mean, if we were to feed in the same sentence, wouldn't we always just get the exact same output? Well, we don't. You're probably wondering why. We don't get the exact same text because when we're generating with a neural network model, we do this thing called sampling. Now, what is sampling, you may ask? Well, the idea is that let's just say we have some output from the network. The network never tells us this is the word that I want you to put next. Right? It's a mathematical model. It can't choose a word. Rather, it assigns a probability score to every single word. That probability score enables us to determine which ones are more likely to be the next word. Now, currently, the way this CoreML model works is that we are just greedily choosing the word with the highest probability, and we're just putting that up next. And neural network models like transformers, or just generally language models, do this thing called degeneration. And degeneration means that after a couple of tokens, they no longer generate any kind of competent output. They simply are incapable of generating good output greedily after a certain point. And that's what we saw just now. It starts repeating itself. We still don't know exactly why it happens, by the way. This is a problem of active research. There are a couple of solutions, but they're really compute intensive, and nobody really wants to use them. So we're stuck with this problem. And that's why, instead of just greedily saying, all right, which word has the highest probability, instead what we actually do is we sample from the probability distribution that the network outputs. So if it says that, hey, I just bought a, and the next word could be house or car, even if it's 70% sure for house, 20% sure for car, and then 10% distributed across everything else, it will actually go ahead and instead of just choosing house, we might choose house or car or something else based off of its probability. So that's called sampling. Currently, though, the way that this model works is we're doing a greedy sort of picking of which word comes next. So in order to fix that, we can change the decoding strategy to be top K. So we're just going to take a look at, for example, the top 5 outputs from the network and choose from them as a probability distribution. So now, when I go ahead and run this model, we should get much better output. All right. So let's go ahead and say, I love deep learning technology. Put a space there, let GPT generate what it wants to generate. This time we should get different output. There we go. So now we're seeing, and this is why we need to make it easier for our students to learn. Interesting. And then it goes to another sentence and says, I'm not going to get into the details here just because I think this is important for our future. And I want, sorry, I'm gonna let this generate for a moment because I do want to see what this is writing, and I do want to be able to show it to you in a moment as well. And I want to make sure it doesn't happen. Interesting. So as you can tell, it's not incredibly lexically coherent. Like, it's not gonna, give you text that conforms to all the maxims of conversation and everything, but it is coherent, right? It follows a lot of, oh, there we go. As you can see, it's starting to degenerate at the end there. I think it's very important for all of and so on and so forth. So it does eventually end up degenerating, but that's just how neural network models are, right? That's a limitation of the technology, and also the fact that, well, remember that while iPhones are the most powerful phones, they're still phones, and we cannot fit 1.5 billion parameter models onto here. If we could fit a larger version of GPT onto an iPhone, we would have way better output, but unfortunately, we can't really beat the laws of physics. We still have really tiny CPUs in these things, at least compared to what computers are capable of. So now let's go ahead and pause this for a moment because I want to show you what I just absolutely love about CoreML. Now, that is a special feature called quantization. What is quantization, you may ask? Well, let me actually show you. Let's just say we take this ML model. It's 650 megabytes. Let's say I right-click and I compress. Give that a moment. Should take less than a minute. Well, what's going to happen is we're going to have a much smaller model because we compressed it. Now, here's the thing. iPhones, again, they can get really large storage space. You can get, I believe the maximum is 256 gigabytes on an iPhone. And so you can fit a lot of data on these things. But people all across the world are using iPhones, and you might not have the network bandwidth to download an entire 650 megabyte model, right? So even just compressing it, look at that, that did basically no damage. That was just 600 megabytes. We just reduced like, what, 45-ish megabytes. That's not a lot, right? That's not going to make a measurable impact. So just compressing models doesn't do a lot for us. So how can we make models smaller? Traditionally, when we wanted to make models smaller, we would have to reduce the number of weights or the number of connections within them. And doing that would give us a worse model because now the mathematics behind the actual neural network model don't have enough space with which to learn the task that we're giving them. And so we want larger models, but we want smaller storage space. Those are two fundamentally contradicting goals. So how do we get the best of both worlds? Well, CoreML has a solution, and it's called quantization. The way quantization works is basically, let's just say we have a floating point number or a double number, right? So in my book, I do actually describe the difference between floats and doubles. And the idea is that floats are 32 bits and doubles are 64 bits. So I'm not sure if I can exactly find that page at the moment, but in my book, I do describe that doubles are 64-bit, float is 32-bit. And what that means is floats take up less space in your computer's memory and in your computer's hard drive. Because instead of 64 bits for a single number, you're only using 32 bits for a single number. Now, in a machine learning model, we use 32-bit numbers. So if you can imagine, if we were to double all of those 32 bits to 64 bits, this wouldn't be 600 megabytes, this would be 1.2 gigabytes. And so that's a lot of data. Even just reducing a single double to a single float across all those numbers halves our model size. Now, With neural networks, we don't need 64 bits because neural network numbers don't need to be precise. We just need a lot of numbers. We don't need very precise numbers. I mean, say 2 to 3 floating point or 2 or 3 numbers after the decimal in terms of precision for a neural network is basically the same as 6 or 12 numbers after the decimal. So we don't need all of that extra precision. And with quantization, what you can do is you can reduce those 32 bits down further into 16 bits, 8 bits, and even 4 bits of information. That's incredible. Now, of course, as with everything in life, there's a trade-off. You're not going to get your lunch for free. Right? There is a trade-off to this. And that is that usually reducing precision doesn't matter. Right? You could take a residual neural network for image classification and go from 32 bits to 4 or 8 bits. And usually everything is fine. You have reduced your model size by a factor of 4 and everyone's happy. But with some larger models, like transformer models, they can be a bit more sensitive to quantization, where reducing their size a lot more actually affects their output a lot. So in this case, we're only going to do 16-bit quantization. As a matter of fact, there may be a bit of an exception that prevents us from doing quantization today, but let's try it out, and if it doesn't work, I will show you the code that's necessary to do so you can go ahead and do it for your own simpler models as well. So let's go ahead and take a look. First thing we're going to do is search up CoreML quantization and take a look at the incredible documentation that we've got available to us. Now, what we're going to do is essentially just go ahead and pick out a simple quantization example that we can base our code off of. Yeah, and also this is actually from this repo. This is a wonderful example of what quantization does. Like for example, this pizza with all of its precision. If our goal is just to get across the point that there's a pizza and not necessarily, all the individual little details in a pizza, then this image is just about as good as this one, right? It doesn't matter. We're still getting across the point that it's a pizza. And so this, depending on the level of detail that you need, this could be acceptable. And then if you really just want to get across the vague idea of what a pizza might be, then even this image would work for you. So you don't necessarily need all of that precision. And this is a great slide from the Apple WWDC talk. If we've got billions of possible values in a 32-bit float, in an 8-bit index, we've only got 256 individual samples from those billions of possible values within the weights. So someone's asking, can we please share the URL? Sure thing. I just put that into the Twitch chat. I'm going to put both, as well as the Write with Transformer and the Neural Network Playground links, just so you have them in case you want them. All right. So there we go. We've now got the documentation for quantization. Now let's simply go ahead and quantize these weights. So what I'm going to do is copy in this code, and then we'll modify it slightly to work with our specific example. Again, we don't need to be perfectly on the dot with this one. So let's just say we do quantize.py. Paste this in. I will actually go ahead and explain to you why we have to do this in Python in just a moment, by the way. Alright, so I'm just going to quickly clean this up a little bit. Get the model name in, which we can probably get from Xcode, so I'll open up my Xcode. Get the model name. Paste that into here. How many bits do we want? Let's just say we want to go to 16-bit. And what function do we want to use? Let's use k-means for now, and I'll tell you again what the difference is in just a moment. So we're going to save this as quantized .ml model. All right. So now all we should need to do in theory is run the code. Now, it's possible that something happens here that this doesn't work, and I'll explain it in case we hit that roadblock. But I believe we should be okay. So right now, things are going through. It looks like it is working. So it looks like, okay, quantizing using k-means quantization. Cross our fingers. Hopefully Nothing goes wrong here. Okay, so it's going to go ahead and quantize the layers one by one. So, okay, while this goes through, I might as well explain what my suspicion was of what might go wrong. And that is that there are some kinds of layers that CoreML doesn't fully support yet, as in the transformers might use like a really sort of exotic layer that CoreML supports inference for, but not all of the different tools within CoreML support the exact sort of usage for. And so there could be some layers here that CoreML doesn't support quantization for. Right, so like let's just say there's a really exotic reshape layer, or a batch normalization, or a layer normalization. These sorts of things, CoreML may not support them just yet. So far, it looks like it's all working, which is actually really exciting for me because I want to see just how much we can get this size down to. The estimated size currently is, I mean, if we were to literally just take the number of bytes and half it, we should be around 300 megabytes with nearly the same performance. I mean, that's really good. Imagine being able to double the download time of your application from the App Store. That just makes it all the more likely that users are going to want to use your application if it downloads quicker. It's a better user experience, and fundamentally your app is lighter on the system. There is no disadvantage to running quantization if you're able to get very similar or the same performance at the end of the day. Now, one more thing is that quantization is more than just doing a sort of blind chopping of bits, right? So usually, you know, when you want to, let's just say, convert a float to an integer, you just blindly chop off the decimal, right? You're not rounding, you're not doing anything smart, you're just blindly chopping it off. And the issue with that when it comes to neural networks is that you're losing actually quite a bit of information if you just chop off a lot of precision at the end. And so what we actually do is, in this case, I told CoreML to use an algorithm known as k-means optimization. And so what that's going to do is it's going to take all the different weights within the neural network, and it's going to plot them out into this sort of space, and it's going to cluster them into 256 different clusters. And then it's going to take the centers of those clusters and all the different weights that are within that cluster, it's going to transform into the center weight of that cluster. And so instead of just blindly chopping it off, we sort of merge similar weights into the same weight. So it's better than just doing it blindly. So that's just incredible. Look at that. We went from 652.6 to 326.3, exactly half the size of the initial model. Now watch this. Let's just say we go into Xcode. I'm going to go ahead and delete my model, so I'm going to move it to the trash. I'm going to go ahead and take this quantized model and plop it right into Xcode. So go into Mission Control once again, copy it over, give that just a moment. This should even take less time to process too, because I mean, think about it, it's half the size. That's less stuff that Xcode needs to compute with. All right, give that just a moment. There we go, it's loaded. Now let's take a look at what Xcode says about this. So pretty much the same layers, same predictions, same utilities, same everything, except we've halved the size of the model. Now let's see how it performs. Do we get similar performance, or do we get something worse? So we changed the name of the model, so I'm going to need to change it in the code as well. So let that go ahead and run. And there we go, it's running. I'm gonna say, I love deep learning technology. Let's go ahead and generate with GPT, and let's see what the quantized model has to say. All right, do we get anything yet? All right, there we go. So it ends the sentence with a period, then says, I'm not sure if you know it, but it's a huge leap from the old-fashioned way of thinking. Wow, that is so just to give you a sense of perspective here, this neural network is not only able to generate text really nicely, not only is it able to generate this superbly. Okay, look at the next sentence. Deep learning can be applied to anything, and you can use it to solve problems in any way you want. From solving complex problems. Okay, there we go. So it's starting to degenerate at the end a little bit, but to think that the quantized model with half the size is performing the same as the previous model, I think is absolutely incredible. So, honestly, just for the sake of curiosity, I must say that I really wish to take a look at what 8-bit quantization would do to a transformer model. So to sort of answer and feed my curiosity, as well as I'm sure your curiosity, I'm going to go ahead and do it. We're going to quantize to 8 bits. Also, unfortunately, for you power men, I know you're running on a Linux VM. Quantization is only available on Mac OS as far as I know. I don't see why they would need to do it on Mac OS only. I don't know exactly what libraries they're using that only let you do it on Mac. But as far as I know, it only runs on Mac OS. So that is a bit of a limitation. Also, I do see that you mentioned, okay, so we need the sklearn package for k-means quantization. So let's install that. Sudo python 3-m pip install scikit-learn. Wonderful. Okay, so we have the scikit-learn library installed. Let's see if Apple likes it. Okay, so it says that the scikit-learn version is a bit too new, so hopefully it still works. If not, then we will install the exact version that CoreML wants. All right, so while we wait, I would love to answer any questions. We've still got some time, so feel free to put any in the Twitch chat. I'll go ahead and answer them. Right, it could be quite literally any question. I mean, about what we're talking about today. It could be about neural networks. Could be about iOS. Feel free to ask any questions. Okay, so yeah, we need a very specific version of scikit-learn. So let's go ahead and implement specifically 0192. Yeah, CoreML tools is a bit picky about what versions of what packages it requires, so it's fine. Someone's asking, did you get access to GPT-3? Unfortunately not. By the time that I had actually heard about GPT-3, I had filled out the survey, and unfortunately, it was too late. They're not really giving out many of those tokens anymore. But hopefully in the future, and actually, while we wait, I might as well go ahead and sort of talk a bit more about some of the limitations of these models. The GPT series of models are pretty impressive. I will say it's impressive to see how they were able to even architect the machine learning systems, or not even machine learning systems, architect the computers themselves, the computer architecture to be able to train models of this magnitude is pretty incredible, right? I gotta say that first of all. But something to sort of add on there is that I feel like people really overestimate the capability of these models still, right? We went from a couple 10 million to hundreds of millions to billions to 100 billion parameters, but the issue is that even though OpenAI continues to scale the number of parameters, we're still fundamentally training them with the same objectives and with the same mathematical foundation, and that is incredibly limiting. The way that these models are trained today is by using something called maximum likelihood estimation. And maximum likelihood estimation is sort of like just saying, predict the next word in the sequence, and become really good at that. And neural networks are generally okay when it comes to, predicting certain attributes that they weren't trained to predict. So, the conventional thought of these language models is, if we train them to predict the next word enough and good enough, then they're going to learn a bunch about the world. They're going to learn how to reason. They're going to learn how to, write very well. But that doesn't necessarily translate. and they end up learning just how to become really good next word predictors. And the more parameters we throw at them, the better they are at predicting the next word, but they're still not creating this internal representation of the world in the way that we want them to. So I would say that they're very powerful, they're really good, but we need new training algorithms. We don't just need larger and larger models, which is what people are doing today. We need better models. We need to work smarter, not harder in a way. Right? We don't just want to throw thousands more TPUs at the problem. We want to throw thousands of TPUs at a better solution to the problem. Right? So that's what we want to do. We don't just want to keep scaling into something that we know fundamentally isn't giving us the results that we want. A great example, I think, would be maybe, let's see here, music recommendation, right? Like, there's lots of examples where, or one of the examples that I like personally would be, let's just say you take a song and maybe a cover song, so like another artist's rendition of that song. Well, the original song has fundamentally different vocal frequencies and a tune to it than the other one. So if your neural network model is only looking at lyrics, how's it going to determine things like vocal frequencies to do music recommendation? It can't. You're not feeding it the right info. You're not training it the right way. So when we start to really train these language models the right way, then I think we can solve problems like degeneration. We can, get better language models once we change fundamentally the training objectives. So that's where the field needs to evolve. All right, so we're still quantizing the token embeddings layer. Let's see where that gets us. Again, this might actually take a bit more time to quantize to 8 bits because 8-bit quantization actually uses k-means. 16-bit was just precision reduction. But then when we go to 8-bit using k-means or this other algorithm for quantization becomes really important. So give that a moment. Gonna let that go through. In the meanwhile, again, any questions about what we just did, feel free to ask. One thing I might actually end up trying, which let's just do that now because we're waiting anyway. We were running all of this compute on the simulator, which was using an Intel chip, right? So I'm of course using an Intel Mac because the Apple Silicon Macs aren't out yet. Soon though. But what we got to do is check out the same performance on an iPhone, and let's see what that gives us. So what I'm going to do really quickly, actually, is I'm going to stop running it on my phone, and I'm going to edit it so that we build in release mode, so it's faster. Because then we actually end up optimizing the code and, actually telling Swift to make it fast. Otherwise, in debug mode, Swift is slow. It's usually slower than Python in debug mode because, then you've got to do all the extra compute of just logging debug info so you can actually, debug your code properly. But then once you go into release mode, then Swift unleashes the whole LLVM optimizer, and just like that, your code is super fast. So give that a moment. Oh, looks like I'm going to need a USB-C to lightning cable, which I believe I have, or even just a regular lightning cable that I can use to connect. Usually, Xcode connects to the phones wirelessly. I do not know why it's asking for a specific cable today, but that's what Xcode's asking for. So we'll test that out once I get that cable. But for now, we can go ahead and get the lightning cable. So all right, wonderful. Okay, so now what I can go ahead and do is plug in my phone to my computer. Let's see what performance we get. So hopefully we don't need a software update for this. Let's see if Xcode is fine with us just winging it. Okay, so Xcode is currently doing a little bit of pre-processing before we can actually run the application, so it's copying cache files. Give that a moment, then Xcode will finally let us actually run the app. So give that a minute, and then we'll go ahead and run the app. In the meanwhile, the quantization is still going strong, so we'll give that a second as well. Also, it looks like my webcam is paused for some reason, so I'll just restart that. Oh, no, that's my charger. All right, hopefully you should be able to see me now. Nice, okay. But let's see what Xcode's doing. Oh, Xcode is done copying cache files. It looks like it should be running the app on my phone. I mean, even now, the fact that Xcode is taking these many seconds to copy the model to my device is telling, because it's 300 megabytes. That's half the size of what it was before. So, oh, camera's frozen again. Optimize is back on stream. Come on, why is that? Let's re-plug it in. Am I back? I'm back? Okay. Well, hopefully it doesn't freeze this time. Okay, so now I'm going to go ahead and open up QuickTime, open up a new movie recording, and then I'm going to switch over to my iPhone so you can take a look at that. And I'm actually curious, what kind of performance do we get on an iPhone XS Max? Something that I will do quickly is do... Oh. All right, so also one more thing, just so you know, really quickly, fun fact, since we're using SwiftUI, the application automatically detects and switches to dark mode on iOS. Anyway, so turn off low power mode. Okay, so I'll tell you why I turned off low power mode in a moment. So go ahead and enter in some seed text. Let's just call this I love deep learning technology. Okay. Generate with GPT. And let's see. So, hold up for a second. Generating text on an iPhone is faster than generating on a Mac. And you're probably wondering why. This is a phone. It's using passive cooling. It's got a case on it. Still, this Mac, that also happens to be running a stream in the background, but apart from that, this Mac, with active cooling and an Intel desktop class processor, is unable to reach the performance of an Apple Silicon chip on an iPhone. Why is that? Well, it's because I believe, well, yep, there we go. That neural engine. Yeah, you already guessed it. Chat got it right. Frantonio1 from the chat and Optimized, both of you got it right. It's because, the future of compute is not just really fast general purpose processors, it is really fast specialized processors, like the neural engine on the iPhone that's just blazing through GPT right now. One more thing to note, quantization does not improve the speed of your models. It only improves the amount of space that it takes. So it only reduces the amount of space. So what's happening right now is on the phone, we're generating text really fast. As you can tell, it degenerates towards the end, but still, it's a pretty great model. Or actually, now that I think about it, it's not degeneration. It's that we're not giving it a long enough sequence length. If I go ahead and feed in a larger sequence length, in theory, we should be able to... Optimize says maybe you should get a specialized processor for your webcam because it's frozen again. Well, I think that's actually more than likely because I plugged in my iPhone as well, and for some reason it doesn't like my iPhone and my webcam connected at the same time, but let's see. Okay, so I'm gonna write that. This time it shouldn't degenerate in theory, or it would crash. Either one. Oh, yep, it's just crashing. So, for the sake of why not, let's do this. First of all, the quantization was taking way too much time, so I'm just gonna kill that. Actually, I'll just keep it running in the background, but instead of k-means, we'll just do a linear quantization, which is, or at least it should be less compute intensive. So Python 3 quantize.py. Keep that running in the background. Something that I will do though is I'm going to go into Swift CoreML transformers and into model generation. I'm going to modify the script to take in a sequence length of 256 instead. And give that a moment. I'm going to let that translate again. So basically what I just did is I made it so that the model itself, when we convert it from Python to CoreML format, instead of treating it so we have a sequence length of 64 and beyond that it just cannot look at anything, I made it take a sequence length of 256. And so it should be able to look at more text, and it degenerates way later. All right, quantization is finally going through. So who would have guessed? Linear quantization is way faster than k-means quantization. But in theory, k-means should be, usually for most models, better in terms of performance, like accuracy, not performance, accuracy. So again, it's the trade-off that you want to make. Are you fine with running your Mac overnight and letting it quantize overnight? If so, use k-means. So there we go. The 8-bit quantization is done, and we got a model that's just 164 megabytes. But I'm not so sure of how well it's going to perform. I'm pretty sure it's not going to be very good. But you know what they say. We really won't know until we try. So I'm going to go ahead and feed in the ML model into my Xcode project. This time it should import relatively quickly. Or about the same time, maybe. Let that go. Until then, are we done our 256? Okay, we're done the 256. We'll take a look at that after we take a look at the 8-bit version. So I'm going to go ahead and run this on my iPhone. Build failed. Oh, we need to rename the model. Let that go through. All right, my webcam looks like it's back. That's good. Watch, right as I say that, it's going to freeze. But all right, so it's copying over the weights. I'm going to show you what's happening on my iPhone. All right, let's see what it says. I love deep. Oh, I also have to make one more change. Move this back to the original sequence length. Give that just a moment. All right. I love deep learning technology. Let's see what it says. Yeah, pretty much as I guessed. It definitely is not as good. Yeah, the 8-bit model is lackluster, to say the least. Or maybe we just got some bad luck with the sampling, although I highly doubt that that's the case. We're going to run this one more time, just in case. Let's start with something simpler this time. How are you? Not too bad. Not too terrible, is what I'll say. I will also say that, well, if you're going through the trouble to make a GPT level model, then in general, you probably wouldn't want 8-bit quantization. So I would recommend that if you're using a convolutional neural network or something that is fine with lower precision, absolutely go for it, because we went from 600 to 164, or 650 to 164 megabytes. That's incredible that we can do that. And as you can see, it's degenerated. But if you're using a model like a transformer that requires extra precision, then at that point, it just makes sense that you would want to use a higher precision model. Even 16 bits, I mean, it was pretty good. So it makes sense that you would want to use more precision. Wonderful. So in today's live session, we've covered a lot of different stuff. We've covered, how to quantize your CoreML models. We've covered how you can infer with CoreML models, specifically language models on iOS. We've talked about some of the special CoreML features. We've talked about, the basics of deep learning and machine learning, as well as, how and why language models work. There's a lot of really interesting stuff. In case you are actually interested in more about language models, I do have a keynote for We Are Developers Live Week in a couple of days, so feel free to join that one as well. I'll be diving a lot deeper into language models, why they work, how they work, some of the cutting edge in non-autoregressive language models, so language models that don't just predict the next word. Thank you for joining, everybody. I see Optimize says this is really fun, so thank you for having fun. I hope this was helpful. And so if you want to go ahead and create amazing applications and learn how to sort of get up to this level where you can use the power of Swift and do a lot more, feel free to read my book, Hello Swift. It teaches you all the basics, everything you need to know about the world of programming, gets you into the world of iOS app development, all the way from not knowing how to program to being able to build simple 2D games in SpriteKit. So this will help you take off to become an iOS programmer. It works for absolutely anyone. Could be a beginner, could be someone who already knows how to program, a kid, an adult. Really open-ended. Feel free to go ahead and read that book, and I'd love to sort of help you out as well. So if you have any questions, if you have any concerns or problems, feel free to put them in the authors forum as well for the book. Again, I am active there, so I will be able to answer your questions there too. And again, do join We Are Developers Live Week next week if you or this week in like 6 days, if you would like to learn more about the world of language models too. So wonderful. Thank you very much, everybody. I really appreciate you joining in. Any questions, feel free to reach out to me, and I will see you in the next live stream. Goodbye, everybody.